Okay, so today's talk is about introduction to deep learning. Know that machine learning in AI is actually grown to a tremendous pace at the recent 10 years. Okay, and now people are talking about deep learning. Deep learning, what can deep learning do? So before that, let me introduce what our rules for deep learning. Some of the slides is actually obtained for all these people. So when we talk about deep learning, these are all the 5 people that is definitely really involved in deep learning. So he's the one who brought in GPU to deep learning. Then we have Yang LeCun. So he's actually a French name, so it's Yang LeCun. So he's actually a student of Jeff Hinton. Yang LeCun now is working with Facebook. For Facebook is actually managed by Yang LeCun. So Jeff is called the father of deep learning. So later you look at the slide that a lot of things is actually started by Jeff Hinton. Then we have Joshua Benjo. Okay, he's the one who started the library, Piano, which a lot of people are using now. Then the new one upcoming is Andre Kashkar. These are all the so-called guru of deep learning. The slide is actually obtained from all these. Okay, so this is the outline. I'll talk about brief history of machine learning, understand how the human brain, neural network, okay, how to implement and what's the challenges. Then advancements of neural network, we have restricted Boltzmann machine. Then the current neural network, and research of deep learning. Then you want to do deep learning yourself, what's a platform, framework, library that you can use. And that's a short demo to show you. Okay, so in the past 10 years, machine learning is tremendous progress. Okay, the recent success can be attributed to what? Okay, in recent 10 years, data is a lot of data generated. A big data area. Chip computing CPU and processing power of GPU is also much faster compared to CPU because of the cost that it has, and a recent improvement of machine learning model. Okay, so now we have a lot of deep learning models, so we can add back to the computing power, and also with the much data that we have. Okay, so with all these current excitement, so we have a new subfield now we call it deep learning. Basically, how does the machine learning work? So before you go to deep learning, how machine basically how example, you want a machine to recognize this as a car. Okay, so you have an old car, you have a new car, and then you have a so-called other type of car. Okay, so what the machine will do is you try to extract all the features of this car, okay, and then all the features of this car and all the other cars that you can see. Okay, then from there you learn what the features of the car. Represent learn. Okay, so for human it's very simple. Okay, but when a computer look at this, it doesn't look at the car. It look at the back of the car, which is pixel. And pixel is all numbers. Okay, so how does the do? Just look at a picture. Which all pixel, you recognize the features, and you can learn that is a car. Okay, so how does a machine get able to learn that? Technique that generally that people learn, the machine will learn, we are quite supervised. It means you have a data set, for example, this is the car, this is the car, this is not a car. In the kindergarten, you tell this is the A, this is the apple, then you show this is not apple. Then the kid will learn. Features, then you learn that machine will learn all the features and you learn to recognize the car. Okay, so the traditional machine learning is all about pattern recognition. So all along last time, all the machine learning is about pattern recognition. For example, you describe all the features of a car, you train the classifier. For example, this is a car. Okay, I take a picture of the car from tire here. Okay, for us, it's very simple. You look at it, this is a tire. But if you look at a computer, it will change everything in numbers. Okay, so how the computer can actually from the numbers, you know that this is a tire and this tire is actually from a car. So same here. So based on all these numbers, you are going to train features and then you're going to classify. Okay. the car and this one. Okay, so it's all about pattern recognition. Okay. So as you go further, you have more and more features, more classifiers you can train. Okay, for example, you have a lot of classifiers you can train. Because car has come in all sorts of formats. There's no one standard. For human being, we already learn over a long period of time, you recognize features. Okay, you look at it, even though a small section of a picture is from a tire, and it's actually so simple. Okay. So basically, you need to have features that you can train. You have features that you can train. So what are the areas that you can train for pattern recognition? The common three areas, which is image. Okay. From a pixel, you recognize all the edges. Okay. You recognize all the texture, the motif, and the part, and then you go out, you recognize the offset. You recognize the text. Okay. You have a machine to recognize the handwriting. That's text. Okay. So for character, you have a machine language and do a translation. Okay. So from a character, you form a word, you do a clause, then from a sentence, then you form. Okay. So then image, you have text, then you have speech. Speech means audio. Okay. So audio, okay, you have a sample, you have a spectral band, the sound. Then from there you combine all the sound, you do your phoneme, and you have the word. Okay. So basically, for any level of training, you need to identify what are the features that you can train. If you do not supply the features that you can train, then you cannot train the machine. Okay. So the image recognition, computer vision, these are all the normal features that people do. Okay, which is scale invariant features transform. Okay, you transform all the features, you recognize all the features. Then you have speed image, HOG, gradient, okay, then you have brief, okay, texture, or radio location, orientation, histogram. Basically, you actually train the machine with all the features that you want to train. All the features that you want, then you can actually train the machine. In the speech, you can expect now frequency, MFCC, you have flux, okay, you have zero crossing rate, all these rules. Okay, basically, you just look at the features, okay, audio or speech. Okay. Whereas for text, okay, NLP, you have parser features, the LER, the tagging, the post-tagging, features. Basically, again, features. Okay, so the features, identify a feature, then you can train a classifier, then you can. Okay, so from here, all the raw data, you do the, then you classify by what ethic that you have. Okay, you have your SVM, support vector machine. Then you can recognize that this is the object that you want to design. Same for audio, same for text. Okay, okay, so the okay, you have to have features. Okay, you have to have features before you can do a proper machine learning. Okay, how does human learn? Okay, how does human learn? For example, how do we learn from when we are kids? Okay, the features to us, but we recognize the features by ourselves. Okay, so you look at the human brain. Okay, so for example, our human brain. Now you are hearing my voice. Okay. The voice goes to your brain, it goes to a part of the brain called auditory cortex. Okay, so you can understand it, you can translate to your understanding. Okay, so the ear pass the sound going, okay, it goes to your auditory cortex. Okay, you can understand my voice. Okay, then the research done that if I disconnect, okay, it's so-called the human wiring from the ears to your auditory cortex, and you connect to your eye. This part of was okay. That means initially it was a part that they actually do hearing. Okay, now because we disconnect the joint and join, this is a real experiment that has been proven. Now the part of the brain, okay, you can learn to see. Okay, you can learn to see. So the same thing happened to other part of the brain. Okay? Have you heard of seeing with the tongue? Okay? Blind people, okay? They cannot see. What happened? They actually wear some type of goggle. So the goggle is a video camera. You actually send back the electronic signal on the tongue. Okay? So what happened? You can train the part of the brain that actually the sweet, the sour, things like that. Now that part of the brain now can see. Okay. The same thing now, if it's a blind, also can navigate around using echo. Okay. Have you seen the people that they can actually know the surrounding by echo? They make some sort of big sound, or they play something with the tongue, something like that. Then they can hear the echo back. Then they can actually feel the surrounding. Means what? Okay. The part of the brain you hear now, you can actually see using that part of the brain. Learn that our brain is very easy to learn, and that's the algorithm in the brain. Okay? Whether it's to hear, to see, to feel, okay? It all, if you give it the same input, it can learn. Okay? If you give it the same input, it can learn. We use this newfound knowledge from our brain, okay, to build a new way of thinking for a machine. Okay? So that's where we have some. So if you look at our brain, look at something like this. Okay. So our brain is a neuron. Okay. So a neuron. Okay. So you have neuron. You have this is a neuron. They call it soma. Okay. Then you have an axon. The axon is going up. Okay. The dendrite is coming. Okay. That means what? If the input signal comes in to the dendrite, the soma will process your axon and send out signal. Okay. That means what we want to do now, okay, no matter what is a problem, okay, no matter what is a problem, we want to build a system that is similar to our brain. Whatever input it comes in, it can learn. Or here, you take the same input and you can process. You can actually build in an artificial neural network. Okay. So the same format. Okay, the same format, you have an input, okay, which is the dendrite. Okay, then the signal, okay, all the input will send a signal, and then you have activation, okay, which is the axon, activation. So the signal comes in, okay, so all the unit here is into a neuron, okay. So in a network, we also represent, we call it neuron, or sometimes we call it unit. Okay, so people say unit or neuron is the same thing. Okay, then this is all your input signal. Okay, so the input signal is all from the dendrite. Okay, so the input signal will come in. Okay, the input signal will come in, and the signal will come in different strength. Okay, the signal will come in different strength, so they have a weight. Okay, so how does the activation of this neuron unit is the summation of all the weight. All the way. So by this concept now, you can actually train the system by all the input that you have, okay, all the input that you have by different weight, then you have an output. Okay, you have an output. Okay, so if you are studying neural network before, I think this you'll be bored to death. Okay. So from neural network, so deep learning is about neural network. The network is all interconnected as a node or edges. So this neural network now can perform complex tasks, just like our brain. Okay? As long as you give all the input, you're supposed to give you some sort of output. Neural network is very structured, and you three kinds of input: the input, the output, and the hidden layer. Later I'll show you the hidden layer. Okay, so each one now will be called a neuron, and whatever in between of the output layer is called the hidden layer. Okay, so you have the input. Okay, then you have the output. In between, we call it hidden layer. Okay, so layers can be many layers. Just like our brain, it's just not just one direction. One layer connection. Yeah, multi layers connection. So how many neurons in our brain? We'll say there's about 10 billion. Model our brain, we can build 10 billion of layers of fluid. Okay, okay, so how does the neural network work? Okay. how does a neural network work? Okay, the first concept you need to know, the neural network has something called forward propagation. Okay, so what happens? The input neuron will receive the input, the data, okay, and then he will send. Okay, remember all the input here, they have different weight. Okay, have different weight. Just like our wave signal, all the input will have different signal strength. Stronger, some will be lower. Okay. Of course, the signal that has higher signal strength, that means you carry more weight. Okay, carry more weight. So the hidden layer will process the output and send the layer to the next hidden layer. Okay. So this will continue until you reach the output layer, where the output layer will determine what is the object classification. Okay. So the entire process is called forward propagation. Okay. So you will ask, how do I start to train the neural network? Okay. So the neural network will be trained. Okay. For example, I have input here. Okay. And then I will output. Let's say you ask the output layer to classify a cat. So you ask all the value here, and then come out the value is different. Okay, what will happen? You need to go back and tweak the network. Okay. For example, just like kid, I tell you this is first time you learn this is a cat. Okay. So when I show you the picture, you say this is maybe a dog. Then you say no, this is a cat. Then you go back and learn again why this is a cat. Okay. So all the input layer through the forward propagation, you calculate a result. And then you get a result, and then the result, okay, the time you train it is always wrong. Because why? Because how do you find out the weight? You randomize first. The first round is always randomized. The first round is always randomized. So when you randomize the weight, the result will be totally very wrong. Okay? So how do you go back and adjust the weight? Okay? So we have an error correction. Okay, we have an error correction. The error correction is called backward propagation. Based on the result that you got, that you received, that you got, what you do? You go back, all the hidden layer, you go back and tweak the weight. Tweak the weight. Then you go and calculate again, see whether how close is you to the result. It's not. Then you go back again to tweak the weight. So to train a neural network of a large label data, okay, you must really compute the difference between the predicted output and the actual output. Okay. So when you get the actual output, okay, whether it's the same with the label data. It's not the same, then you can go back layer by layer and tweak the weight. Okay. So that process is called back propagation. Okay, or we call it back prop. Okay. So during the back propagation, all the weight, okay, or biases will be tweaked slightly until you get the lowest cost. Then we call it gradient descent to get the lowest cost. Okay. So the important aspect of this problem, okay, when we measure how much cost change refer to the change of weight in bias. Okay. Of course, when you have a lot of layers and you have a lot of neurons, more and more complicated. Okay, because the complexity will rise exponentially. Okay? And every time you go layer by layer, when you want to tweak, you get it harder and harder. Okay? So one of the problems with background propagation is when you go to the last layer, this one. Go into the last hidden layer. When you go into the last hidden layer, because when you back propagate, you start from the upper layer, you tweak here, the weight, you tweak until you get to this layer. Normally, when you get to this layer, your difference is very small. The weight is different, very small. Okay. What will happen? You take a long time to find the best weight. You take a long time to find the best weight. Okay. So this is one of the problems with neural network, because many layers, okay, towards the end, okay, the training time will be very long. Okay, so neural network is not new. Okay, it started around I think 1980s, something like that. Okay, so during that time, okay, people not very excited about neural network. Okay, why? Because of the backward propagation. So during that time, okay, we don't have a lot of label training into that. Okay, because towards the end, it's still supervised learning. Okay. So you have a lot of data not labeled. Okay? So you don't have labeled data, then you cannot use neural network. The learning time did not scale very well. Okay? Because it was very, very slow, especially when you have a multi-hidden layer. The more layers you have, you need to train. Okay? And sometimes you start at local optima. If you do machine learning, local optima means it's not the lowest cost, but it's actually a local cost. Okay? A problem with neural network. Okay, so now, okay, how do we move forward from neural network where we need to supply the features, okay, features and the label data. Okay? So what is the method now that we can actually start this neural network without label data? How about we have a machine that can identify the features by itself? We have a machine that can recognize the features by itself. Okay, so with that, Jeff Hinton, okay, so this is so-called the father of deep learning. He actually come up with this machine called restricted Boltzmann machine, RBM. So it's actually a very shallow neural network, just 2 layers. Okay. The input layer, hidden layer, go back to input. Okay. So very simple. So there's only 2 layers. Okay. So RBM is very shallow neural network. There's only 2 layers. Okay. One visible layer and the hidden layer. Okay. So what you do? So very simple. You can actually randomize the weight. Okay. You randomize the weight, you get the activation from the hidden layer. Then what you do? You work backward. Okay. You do a weight. Then what you do? Okay. So then after that, you actually measure back the weight by itself. Here, the restriction here means what? There's no 2 nodes from the layer share the same connection. So how does the RBM work? Okay, how does the RBM work? Okay, so the goal of RBM is to create input as accurate as possible. Okay, so during the forward pass, all the input will modify the weight. So you have a random weight, we activate the hidden layer. So now you get a result. Okay. Then from the activation layer, what do you send back the result to the input layer. That means what? You get the input, you get the go to the activation, now you send back the weight back to it. Why? Because this is your input, you get a weight, you go to activation, then you get a result. So your result should be the same with your input. Okay? Now we'll try to modify the activation based on reconstructed from the original input. So very simple concept. I tell you something, you learn. Yeah, you tell me back what you learn. If it's wrong, I tell you that this is why you're wrong. Then you tweak again. Okay? So from there, RBM is always trying to reconstruct it, and then the data do not have to be labeled. Okay? So what is the main advantage of having RBM? Learn the features by itself. Okay? You can learn the features by itself. So RBM can be something called a feature extractor. Now you can actually group the features together, okay, and we call it encoder. Okay, so sometimes RBM also known as auto-encoder. Okay, auto-encoder. Okay, two-way translation machine. I translate it, I calculate all the way, then I translate back to you. Okay, then you draw, then I tweak it. And from there, I can learn the features, okay, of the input. Okay, so now we solve the problem where we do not need to provide label data. Okay, we can use RBM to extract the features by itself. Okay. Okay, from there, okay, they actually stack up the RBM. Okay, remember RBM is only two layers in it. Two layers. So the output of the RBM will be an input for another layer. So the input of the RBM, the first RBM, will be the output of the first layer. Okay. So by stacking up the RBM, okay, okay, we can build a more, okay, we can build more layers of network where we call it deep belief network. It is where the deep comes from. Okay. So deep belief network, okay, is actually used by Google to do their image recognition problem. So Google is not using deep learning; it's already started to use deep belief network. Okay. So DBN is actually trained by 2 layers at one time. So basically, it's like RBN. Layer is 2 layers. Okay, it's stacked up of RBN. Okay. Instead of you providing all the features, okay, so the features is extracted layer by layer, automatically by RBN. So throughout the net, the hidden layer of RBN will act as an input of the next layer. So the first RBN will be trained, output then will be input to the next RBN. This procedure will be repeated until you have an output. Okay. So from there, you see there's an image. Okay. You have a 5 neuron, then you stack up all the RBN, then you have another 5 neuron. After that, you get your result. Stack up RBN. Okay. So deep belief network, what you can do, you can actually recognize patterns inside data. Okay, so basically it's actually a multi-layer features extractor. Okay, so the unique aspect of this network is all the layers will end up all the full input structure. Okay. So the layers will learn progressively all the complex patterns like the facial recognition, and every layer will detect all the edges. And all the edges will combine them to combine the features. Baby, we learn that this is the normal face feature. Then from there, we learn the eyes, the ears, okay, the mouth, nose, everything. You are a whole complete facial features. Okay, so DBN can learn all the hidden patterns globally using the camera. Slowly bring the object into focus. So towards the end, okay. As you can see now, we can learn the features of a feature, but you cannot recognize whether it's a human or not. Okay. So towards the end, you have stacked out DBN, at the end, classifier. Okay. You still need a classifier. Okay. So the classifier will be a label, okay, to result of the pattern. But now, because all the features that you have, your DBN require a very small set of label data. Or neural network, we have huge label data. Okay? So DBN is a fine-tuning supervised learning where you only require a small set of labels. So something like this. Okay? So we have a raw data. You expect all the low-level features. Then you expect go up one level, mid-level features, all the eyes, the nose, the mouth, everything. Then you have a high-level features you can actually recognize. Okay. So your input, all the hidden layers, and then towards the S, okay. This is a keyword. Okay. But the features is extracted using your RBN. Okay. So from there, okay, we move on to something very popular now. Okay. One of deep learning, one of the most used network is called convolutional neural network. Okay. So the convolutional neural network is actually inspired by our visual cortex. That means by our the part of the brain that processes our things. Okay. So CNN, okay, is a deep net mainly used for image, object, or even speech recognition. Okay. So it's actually pioneered by Jan Leku, by Unix. So Jan Leku, like I said, itself, he was actually a postgraduate student under Jack Hinton. Okay. We have a deep network, okay, which are all generally very difficult to train. Okay. So now what will happen is the CNN will have a multi-type layer, where the first layer is the convolutional layer. I'll give you an example how does it work. For example, let's say this is a speech and you want CNN to recognize the image. You want the computer machine to recognize. Just look at this. This is a bridge. Then you have something like water or sea or lake, whatever, and then probably you can recognize this is a San Francisco Golden Bridge. Okay, very simple. convolutional neural networks. Okay, something like this. Okay, imagine you divide your image. Okay, imagine you divide all your image. Okay, it's like a flashlight. You have a flashlight that shines every single part of the image. Shine to every single part of the image. And every flashlight now can be represented by a neuron. Okay, can be represented by a neuron. So what will happen? Okay. So now, for example, this flashlight here. Okay, what will happen? You can actually pass the features, and inside this neuron now, you can have that you want. Okay? For example, you want to extract certain patterns. Okay, you want to extract certain patterns. Okay. So what happened? For example, you have the filter 1, filter 2, filter 3. So every filter now you can fit in one neuron. Filter you can fit. From there, okay, you calculate the weight. Okay. Remember, towards the end of neural network, everything is about weight. Okay, how much, for example, for this flashlight here, okay, how much of this weight, okay, that you can calculate for this filter or this filter? Okay. Obviously, maybe for filter to this weight here. Okay. More weight from that pair. So this part here is where we call the convolutional layers. Okay. So the first filter will form the layer 1, which is a convolutional layer, where all the weight and bias will determine the filtering process. When you look at the part of a picture and contain human face, we look at what are the patterns for every single part of the image. Okay. That part is what we call convolution. So each flashlight now, it can be represented using neurons. The neurons were activated. Okay. Convolution layer now will look for patterns. Okay. That means now you look for patterns all over the image. Okay. Look for patterns for all over the image. Okay. So the pattern now searching through the process called convolution, and then the neuron for every filter will search different patterns, and then it can process and input them. Something like this. Okay. So you have all the weight, okay, all the weight coming. You have the convolution layer. Okay. You recognize all the image. You have a pooling layer. Then you do all your neural network training. Then you have a software layer. Software layer basically is the probability to calculate what is inside that layer. Okay. It's a software layer. Okay. So what is the application for CNN? Okay. For CNN. So CNN has been used widely now to classify a scene in an image. Okay, to classify a scene in an image. Let me show you this. Oops, there's a look here. Oops, computer hack. For example, wait, there's something, for example, there's a, okay, for example, this research done by MIT can recognize a scene of an image using, so I can actually go to the demo here. So I can upload an image or I can use the existing image, For example, take this image. So he will actually, and then he will recognize this image. Whether this is the image that I passed through, then he will say, this image is an outdoor image. It contains skyscraper, 0.6 probability. It contains tower, 0.27 probability. It contains office building, 0.09 probability. And the scene is cloudy, open area. It's a man-made area, natural light. So basically, you can actually describe the image. Okay. So you can actually use the CNN again. You can see filter all over the image, and then you identify the object inside the image, and it can tell you describe the image. Okay. So you can actually try other demo here. Okay. They all basically use the CNN to actually describe the image. Even they can actually now describe the video using. Imagine now you have a live video. Okay. Let's see describe. Okay, this is now somebody is walking around and then they are suspicious. Maybe terrorists, or maybe they're doing vandalism, or maybe, for example, in a house, you can actually detect, or maybe this person is not feeling well, or something accident happened. Okay. So you can actually do video classification now using CNN. Okay, from CNN, we have something called recurrent neural network. Okay. So recurrent neural network is actually by these two persons. I cannot pronounce the name. Okay, so the recurrent neural network has a feedback loop. Whatever that you predict now, so recurrent neural network is very good time series data. Okay, when you have time series data. So things that you learn through a neural network, okay, you can actually pass to the next time. Okay, you can actually pass to the next time, t equal to, t equal to. Okay, so the RNN will receive an input and it will produce output. Okay, so unlike the different network, the input output now come in sequence. So everything the time you can t equal to 1, t equal to 2, t equal to 3. Okay, so what are the good things about that? You can actually use it for do subtitle for the auto subtitle for video. Okay, you see now YouTube now, you just upload something in YouTube, after like 10 minutes, it will auto generate subtitles for you. How does it able to do all that? Using RNN. Okay. Okay. Of course, you see time getting longer, pass to the next layer is about to huge amount of data. It's another technique. It means it's a long term, but only short term. That means what? You discard those are things that you don't want. So the amount of information that you pass to the next layer will be smaller. So that is called LTSM. So where can you use RNN? It is very simple for time series data, where the output is the next value of sequence. Okay. So you can actually use for image capturing, document classification, or you can classify image frame by frame. Okay. So those are things that's very good where you can use RNN. Okay. So we have gone through from neural network all the way to deep belief network, restricted post, convolutional neural network, and RNN. So why is it people all keep on talking about deep learning? Deep learning is very robust because all the features ahead of time. Okay? So features can be automatically learned, okay, by hand, and it's very robust to any different variation of data. Okay? Some of the problem with our data and pattern recognition is we have a set of data, we train the data, but data change, it doesn't recognize anymore. We have a facial recognition with a 9 group. But if it's slightly darker or you slant your face, whatever, then you cannot recognize your face. Deep learning overcome all these variation, supposedly. Okay. Then we have a generalizable. The neural network can be approached for different applications, the same approach for different data. The features, okay, then you can use it. It's scalable now, because now we have higher computing power and also with all this GPU, you can actually parallelize it. What is the weakness? Of course, the weaknesses of deep learning is it requires of large data. Okay, the more the better, but it has to have the long. Sometimes other existing machine learning like SVM support vector machine or other technique will go good result to think whether I want to use deep learning machine learning. If the result is not so much, it's better use normal machine learning technique. Okay? Deep learning tend to learn everything. Sometimes it's very hard to learn what is to encode. Okay? And the feature understand. Okay? Look at the features as well. You cannot understand how you what you learn. For example, all these features here. Look at it, you know what the features have learned. So it's very hard for the human to interpret why these features have been learned. Okay? And then you require, of course, a good understanding how to model all this modality of data, and also what are the tools that you know that can use deep learning. So deep learning has been used everywhere in medicine, media, entertainment, security, defense, autonomous machine vehicle. If you look at the Google or Tesla or the self-driving cars, basically learn over a long period of time using CNN. Okay, so I have a lot of video here. Just choose a few. Oops. Okay, we hang the computer. Okay. So of course, you have learned about AlphaGo. So what happened is they created similar to Google Glass, but this actually to help the blind. Even the actually feedback through as a voice to the example now we're using this live code. We say you just see actually this is the building. So for example, this guy go around blind, then you actually detect the surrounding. Then you go to it actually gives you a voice. There we have the chip box. So you can recognize his face, you say this is somebody in the room. So basically, some sort of live video recognition there. This one I want to show you. This one is also very interesting. Okay, this one is Google Learn to pick up stuff. One of the robots that actually learn to pick up stuff. What happens is the robot you need to pick up the one that actually learn to push it first. So the robot actually learn that sometimes you learn to actually put stuff away and then pick up. Why is it showing cartoon? Last one, I want to show you this one. Called deep. The Google deep learning is called DeepMind. They actually feed the images from Atari game. The image of Atari game. They actually ask the machine Atari game. So the machine will not know what they get the data. So starting from 10 minutes of training, back the ball. But after a while, full score. Several minutes, there's magic happen. Start digging thunder through the wall to beat the equipment. Huh? You learn the pattern. So now you can see now, going outside, then you keep yourself. Okay, so there are more videos. Just if you want, you can go and see. Okay, so what is a deep learning development cycle? So basically, okay, you need to train your data set and select your training data set. Train it, okay. After that, okay, deploy it, do the classification. If there's okay, and then retrieve the weight. Okay, so if I want to do deep based process, so they help me to provide everything for you. Yeah, platform. Then H2O. H2O now available interface. I have done testing to learn the. It's just train about 45 minutes to actually recognize the language. Then there's a framework, Cafe. Cafe framework is for locally vision. Research now I'm using Cafe. Hoong is machine learning that I think they support GPU, but it's programming language called Kuan. Then we have a library, the tester from Google. So it's a library for memory computation. It's actually from Google. Now with Piano, so Piano is a Python. So if you any coding in Python, then you can use this Piano. Okay. So all the model now being used, being trained. Okay. If I have a model that I already trained, okay, so I can actually share the model. You don't need to go and build multi. You can just train it on your data. Okay. So existing model, we have Alexis, who learned that actually from a younger group because then we have half also. All these models, they put in a big models to share all the models. So start deep learning. I don't have the time to go and build all the models just use their existing model and train on data. Okay. So this is the content recognition. So it's actually a data set that I done. So we actually work on data in post office in America. So all the post office now, last time, they need people to recognize the postcode. Okay. So what happened is I'm going to take up this and train up using neural network. Okay. So all the handwriting, you actually build a database. Okay. So you can actually now use your deep learning or machine learning method, whatever, to actually train the features of all the handwriting. Then you can actually recognize the handwriting. Okay. So today I'm going to just demo a very simple one. Okay. Handwriting network model, training model. Okay. So the next is a convolution you can recognize visual pattern, writing character. Okay. So it's very robust with distortion and even trick transformation. So even your handwriting a bit distorted, you still can recognize it. So this is CNN based and for machine learning, actually goes through this. Okay. The one that I want to demo is using NVIDIA DGIP. DGIP stands for NVIDIA Deep Learning GPU Training System. So with NVIDIA DGIP, provide a data set, you can deep learning to apply it to it. If you want, you can go to developer.nvidia.com/digit, or I can demo to you now, or it's still playing this other. Okay, I will set up the server. So the you do not need to do anything. So I use the recording is consumer. Okay, so this is what happened. So in DGIP becomes something like this. So I have the database, the MD database. Okay. So then in the model, I'll use the model which is based on cafe. Okay, based on cafe. So okay, actually now I already trained it. I put in my database now. That's 60,000 handwriting. 60,000 handwriting database. Then I train it within the net. So in the net, we'll get all the features of every single handwriting recognition. Go in, I can see this in my database. Okay. So now, if I want to test an image, I can actually test an image. Supposed to be. Okay, I need to get. Cannot get the image. Okay, sorry, I forgot the URL. Basically, I can show you the image of the handwriting. You can actually tell me what is the handwriting, whether it's 5 or 6 or 7 or. So now with that, I can actually train this up already. So it's very easy. I can actually train it up, and then I can actually get the results without any pulling that. It's quite simple. Don't find the image.
export issue that's supposed to be still. Let me try this. Okay, right. Okay, so basically, you can actually use deep learning, this digit, okay, with all the model, existing model, then you can actually do some training. For example, now let's say you want to classify human face, you can provide a lot of human face, then you learn the features, then after that you can actually recognize the face. Okay, so if you want to use other framework, other model, you can use Diano, or you can use the platform, for example. So that is the end of the talk. Hopefully it's within 1 hour. 1 hour. No question? I forgot to set up the location of the image. I cannot find it out. I can show you there. If you want, you can actually go in there and see and look at it.
This is this presentation. So the neural network is only one that's very popularly
Deep learning is actually based on neural networks. It's neural network. It's yeah, it's so-called neural network 2.0. Any question?
Application using deep learning. You have text, and then
Yeah, I mean the translation now. You can see like Google now, they can actually understand the text. Find out that if it's like a Siri, whatever, or Google now. Okay, because after a long period of time, we actually learn the way they talk. Intonation, whatever, even different slide. That's the features that have been extracted. So they extracted, you can actually feedback into the neural network, then you can actually learn better.
The example that you gave earlier recommend that the environment. I found it interesting that the semantics also you can really straight away learn, right? Like when we look at image retrieval and all that, usually they learn the low level, mid level, high level, all separately. That means is deep learning. I don't know how neural network works like we use it. So is it that they are utilizing more stable image which is within the deep learning? Like is it an engine? Is it an API? What is it that makes it able to learn?
I think it's the features. They are able to extract the features.
Maybe it's applying some kind of stable algorithm to get the semantic.
It's like this. When you extract the features already, then you pass it to your small training data set. Okay. There's a data image that actually, if you go to Google, you actually classify. People do image recognition, they know. ImageNet. So ImageNet is a data where we actually classify more than 1,000 vectors. 1,000 category of image. Okay. So your image recognition, you can actually how to say
so it's leveraging on existing models
yes.
for image identification, low level, whatever, and then.
So if you upload an image that is not inside this 1,000 category in ImageNet, you say you don't write it.
So if you're configuring deep learning, normally other machine learning, we do the extraction with the text, we display the data. So for deep learning, what would be the input format? We define these models that you should leverage on, or
define what context you're looking at, what data is.
Like the image one.
Yeah, image one, what is you have to there's not a flashlight I do in it. You actually have to split it to 28 by 28 small rate.
So we have to do that.
You do that, then you will fit in, then every single 28 by 28 pixel image, you actually find the pattern inside that.
You go up one level up, and you find a bigger, higher level features. Then after you can actually learn that these are all the patterns, that all these patterns, these features, actually is object.
Which means the extraction part we are still doing. The training set that we create, right, without enabling doing the extraction of the basic features or something.
No, those features are done independently.
I think so. It just points to a model to extract it for us, I guess.
Your model means what?
Retriever, like if you want to extract low level features, there's so many algorithms out there. Right? So is it that when we point to that one and
the model that I refer is how many layers that you want.
that's the, I mean, I understand the deep learning structure, but then the initial training set, then I just give the image. So that means when
you never specify an image, then you actually tell you extract it.
you just use it like black box.
It's something like black box. Just so one of the written article with deep learning is very successful now. They can recognize object or see whatever is in the image. We also suffer with our visual context. These are how we see it. We suffer the same thing.
So
sometimes
our role is only giving it then everything else is
your role is really to do the modification because you have a small label data set. You use a small set to train
sure that
the training part, then actually use it.
I think we will need more towards classification. Clustering. Big cluster, like the images, cluster.
Actually, the word for deep learning towards AI is still pattern recognition. It's still finding patterns.
yeah.
It's still finding patterns.
But I'm just wondering, the black box, I think that we don't tweak it's just something, unless
Yeah,
you're doing research.
you tweak, yes. When you're doing research analysis.
If I'm doing research, otherwise I'm just using
Yeah, that's why the teaching one, you're not just
layers. You can get how many layers? What is the training of
that.